Ladies and gentlemen, after some minor technical difficulties, this is Felix von Leitner on Big Num Arithmetics. Give him a warm welcome.
Well, good morning. Thank you for coming in this large numbers at this time. Unfortunately, I have a new notebook, and although I tested it on a Beamer and the DGA how it works, the Beamer here doesn't like it, and now I have to use this Apple computer. Just kind of ironic. Okay, so I will be talking about Big Num Arithmetic today. Okay. So every one of you has probably used Big Num Arithmetic, and many of you hopefully wondered how it's actually done on the code level. How do you write code that works with big nums? And I will talk about that today. Usually when I say big num, I mean 1024 bits and up. I will not talk about how RSA works, or about how AES works, or what exponentiation is. I hope you know that. And the agenda will be, at first, how to represent big numbers in a computer, then how to add them, how to multiply them, and then the most important part for cryptography is how to operate on modulo operations. So the first question is how to actually represent them in a computer, and the normal numbers are represented with 2's complement, so that if you subtract 1 from 0, you get all the bits set, and that's the representation for -1. And that works if you have all the numbers have the same length, because then you know which bit is the most significant bit. But big nums can have varying length. If you add 2 big numbers, you get the bigger number, right? So this is dynamic, and this doesn't work out, so no one does it like that. The next idea would be to have COBOL-like arithmetic that was used for accounting, and they didn't use that for speed. They used it so that they wouldn't have rounding errors. So it works, but does not scale at all. So what everyone does is using absolute numbers and a sign bit and put that in a struct. So I have some examples for this. So usually you try to have an array of integers, unsigned integers, and have the biggest integer type you can have for each limb. And the idea behind that is that some algorithms, the important ones, don't scale linearly with the number of limbs. So if you do a multiplication, you get you have to do work to the square of the length number of limbs in the big num. So if you have smaller limbs in the big num, then you end up doing more multiplication. So you want to have this as big as possible. And the canonical biggest integer type on the machine that fits in a register is size t, so that's what I'm using here to describe this. The same basically for gcrypt, which is used by GNU-TLS, that's why I have it in the list here. You can see that the array is usually allocated on the heap. So you have some kind of bookkeeping stuff, how much you allocated, and GNU-PG gcrypt has this flags thing, which is kind of funny because they write down if this is a secret number, and if it is, then before freeing they zero the space. And well, usually the accounting is more work than just zeroing everything, but you know. Another important big num library is GMP, and they do the same. So everyone does it like this. The first important thing you have to do with big num is adding them. That's one step in all the other algorithms, so this better be fast. And usually the first thing you notice is that if you add 2, you get carry, and it might be just 1 bit, but it's still you may need 1 more limb in the result than you had in the 2 sources. So the size of is not in bytes, but it is in limbs, right? So most CPUs, well, any CPU really has add with carry, but it's not so easy to get this instruction from a C compiler. So the trick you normally use is that you use the double length integer type, which is long, and you cast if you want to add two integers and want to have access to the carry information, then you cast one of the integers to long, and then take the upper half by, for example, shifting right. The problem is if you are on a 64-bit machine, then long is already 64-bit, right? So there is no C data type for 128-bit integers, which is a big issue if you want to implement big num code in C. So GCC has an extension that's called __int 128, but that's strictly GCC. Even compilers that claim to be GCC compatible, like the Intel C compiler, don't have this data type. So that's what my code uses right now, but I mean, all the examples I give in code will be in assuming 32 bits. So unsigned long in this case is the 64-bit type. So this is basic addition. You just go through all the limbs. One thing I skipped over previously, but which is kind of important, is that the order in which you put the limbs in the array. You could have the same as the bits inside one integer. You could have least significant bit first, or least significant limb first, or you could have the most important first. And it turns out to be much easier to have the least significant first, because addition and multiplication go from the least significant one to the bigger one, and the carrying works in that direction too, and the CPU prefetch works in that direction too. So usually it's a win to do it this way. If you have a smart compiler, it will understand that this shifting by 32 bits is not actually shifting, and most compilers do that. But I have some numbers later on how well compilers work compared to assembler implementations, and it's a mess. So issues with adding two big nums is, the first one is it's not parallelizable, because you have the carry between every two limbs. So most modern CPUs are superscalar, so they have more than one adder in the CPU. And if you add two numbers, and each add has to wait for the one before that, then basically you can use more than one addition unit at a time. So this is an issue. People have proposed to use some tricks, but most of them only apply to hardware. So people have, for example, on smart cards, you do big num arithmetic in hardware, or you add some instructions to the hardware to help with it. And there are some addition circuits that have lazy carry propagation, so they try to tune the algorithms so that the part they need first is ready first, but the rest trickles down in the next cycles. But you can't really do that in general purpose CPUs, so I'm not going to go into that much. You can do that in software. People have tried, but it's not worth it. So one important thing is that you can use big num arithmetic to learn more about your CPU than you ever wanted. And it turns out that, in addition, it's not the one adder that bottlenecks the operation, but it's the memory access, even if everything is in layer 1 cache. So then you can see that some CPUs are more suited to big num arithmetics than others, and the most glaring example is the Pentium 4, because it has half a cycle for normal adds, but 8 cycles for an add with carry. And since you have carry in every step in big num adding, you can see that adding is really slow on Pentium 4. Same for multiply. I come to that later. Subtracting works the same. You can understand how that works. You have to figure out the signed bit first, but usually in cryptography you will have unsigned integers, big unsigned integers. So the case where a number can even be negative is only an intermediate result of bigger calculations. So in some cases you can actually skip this whole signed bit stuff, but no one actually does. In multiplication, so the easy method that everyone learned in high school is just, I tried to write it down here, the school method. You see that the result of the multiplication will have twice as many limbs as the source. So usually in crypto the source numbers are the same size, or even more probable is that they are also the same number. So in many cases you don't actually multiply, you square. I have a slide on that too. So this school method, everyone has learned it hopefully in school. It's the easiest one to implement. The problem is that the results of the multiplications have double width. So this CF thing, right? So C and F are already the biggest integer you can fit in a register, so C times F is a long. And if you add two of them, like for example in this column, you see the mouse? Okay. If you add two of them, it doesn't fit in a long anymore. Right? So there's no bigger data type than long. We already tried to choose the biggest one. So the question is, how do you do that? And the dirty C trick is to have two longs and then shift and add the carry yourself, and that's kind of messy. And it's really the stress test for the compiler, because in that case you don't have enough registers to hold everything in registers. So the compiler has to be smart enough to notice that the lower part of the one long is no longer used after that, and reuse the register for the other long, right? So if the compiler were really smart, it would work out, but in practice it doesn't. So also multiplication is quite costly, so it scales to O n squared in multiplications, and what looks even worse on paper is that you have 3 times n squared additions for all the carrying operations. And this is if the compiler understood what I meant and doesn't do any superfluous stuff, then it gets even worse. So this is really costly. Interestingly, if you implement this, it turns out the adds are free, because in the CPU you have pipelined multiplications and superscalar stuff, and during the wait for the multiplication to come back with the result, the adds from the previous round are done. So I noticed this when I decided to do the first step or to all the multiplications with SIMD instructions, so the vector instructions of modern CPUs, right? So I did that, and it turned out that it took even just the multiplication stuff without the carry reparation pass, or whether it's the same data, it was already slower than the whole school multiplication was before. And I was shocked at that. I didn't expect that. So welcome to modern CPUs. So I wrote this down. This is also true for non-vector code, obviously. So if you just do the multiplications and write them to another array, like in this case, it turns out that this is much slower than the routines in OpenSSL, and this is just the multiplication, right? And this the slowness comes from the write back to the temp array. So you see that in modern CPUs, what you learn as assembler hacker in school, or I don't know where you learn assembler these days, but if you learn assembler, they usually tell you that you should avoid jumps, conditional jumps, and you should try to keep stuff in registers. And it turns out that the only thing that's really relevant to getting good performance in modern CPUs is that you do as little memory accesses as possible. So it's really worthwhile to not write or read anything that you can avoid. And I have some statistics on that. So if you keep stuff in registers and you have one memory access can cost as much as 200 cycles, and that's from the layer 2 cache, that's not from the actual memory, that's even worse, right? So just so you see the order of magnitude we're talking about here. So 200 plus cycles if you access memory needlessly. And mispredicted conditional jumps, and everyone was whining about this when this number was published, on a Pentium 4 is like 20 cycles. And if you calculate the peak throughput of the CPU, then you can do lots of adds in parallel, and this ends up to be like 120 instructions potentially, right? But if you see the 200 cycles, that's a whole different game. So it turns out looking at jumps, it does help. So if you unroll loops, it does help, but the code in the loop also needs to be fetched. So modern processors have prefetching for this. So it's not as important that it was. Now we have like double data rate memory, but in some CPUs that are more memory throughput stuff, this is a real issue. So I decided early on that I wouldn't really unroll loops completely, because I thought, it's more important to have this small code in the end. Because you end up writing the significant routines in assembler anyway. So the major issue in assembler routines is that it's completely unreadable usually. So if you have to write unreadable code, you better keep it small, right? So that if someone wants to read it, they have some chance in hell. So multiplication, I told you that adding with carry can take up to 8 cycles. Compared to the 200 cycles, that's nothing, right? So you see the priorities shift a little when you look